Hi there. Welcome to Sleep Stories Universe. You made it to the end of the day. Get comfortable, however your body wants to rest right now. Last time, we followed the quiet clues that revealed a black hole without ever seeing it directly. Tonight, we move a little closer to the boundary that gives a black hole its most mysterious shape, the event horizon. You don't need to memorize anything tonight. You don't need to follow every detail perfectly. Just let the words carry you. Tonight's story is where time slows down. A gentle journey to a black hole's event horizon. We'll move slowly, step by step, through the strange idea of a boundary that cannot be seen, through the way time behaves near a black hole, and through the quiet limits of what light itself can do. And along the way, we'll stay honest about something important. There are parts of this story that science understands beautifully, and parts that still remain quiet and unresolved. And if you drift off somewhere along the way, that's perfectly fine. Let's begin. Somewhere out in the deep quiet of space, there are places where gravity becomes so strong that our ordinary instincts about distance, motion, and time begin to loosen. Not all at once, not dramatically, but gently, until the universe starts to behave in ways that feel far removed from everyday life. Near a black hole, even familiar ideas, like inside and outside, before and after, possible and impossible, begin to shift. And at the center of that strangeness is a boundary with a quiet and unforgettable name: the event horizon. To understand it, we have to begin with one simple idea. A boundary, not a wall. Not every boundary in nature is a wall you can touch. Some are simply the soft edge of what one world can know about another. Think about that for a moment. Most of the boundaries we're familiar with in everyday life are things we can see, or feel, or press a hand against. The edge of a table, the shoreline where sand meets water, the moment a door closes and one room becomes separate from another. These are solid, immediate, physical things. They exist in a way we can point at. The event horizon is not like any of those. It is not a surface. There is no material there, no membrane stretched across space, no glowing edge, no fog you would suddenly pass through. In the language of physics, the event horizon is a boundary in space-time, a place in the geometry of the universe where, because of the extraordinary concentration of mass nearby, something fundamental changes about which directions remain available to light and to matter. That is the heart of it. And because that idea can sound abstract at first, let's stay with it for a while and unpack it slowly. To understand the event horizon, it helps to first get a sense of what a black hole actually is, and how gravity becomes strong enough to create one in the first place. Here's the simple version. A black hole is a region of space where gravity is so strong that the escape velocity, the speed required to break free of that gravity entirely, exceeds the speed of light itself. Escape velocity is something we deal with on a much more familiar scale right here on Earth. To launch a spacecraft fully free of Earth's gravity, not just into orbit, but away and gone, it needs to reach a certain minimum speed. Go fast enough, and you're free. Go slower than that threshold, and gravity eventually brings you back. Every massive object in the universe has an escape velocity. The more massive and compact the object, the higher that escape velocity becomes. For a neutron star, a dense, compressed remnant left behind after certain stellar collapses, the escape velocity becomes an extraordinary fraction of the speed of light. For a black hole, it goes further still. The gravity is so extreme that not even light, which travels faster than anything else we know of, can move quickly enough to escape. This is a prediction that comes directly from general relativity, Einstein's theory of how mass curves and shapes the fabric of space-time. And the boundary where even light can no longer break free, that threshold, is what we call the event horizon. The name carries its meaning almost poetically once you know what to listen for. Think of the word horizon in its everyday sense. Standing on an open plain or looking out across a wide ocean, the horizon is the farthest line you can see, the natural edge of your observable world from where you stand. Things still exist beyond it, but from your position, the curve of the Earth carries them out of sight before their light can reach you. The event horizon of a black hole works on a deeper principle. In physics, an event is simply anything that happens. A collision, a flash of light, any occurrence at a particular point in space and time. The event horizon is the threshold beyond which events can never inform the outside universe. According to general relativity, nothing that occurs inside, no light, no radio wave, no signal of any kind, can ever reach an observer on the outside. Whatever happens in there stays in there permanently and completely. And once any object crosses that boundary, a photon, a particle of dust, anything at all, general relativity predicts it cannot return. The structure of space-time beyond the horizon in this framework allows only one direction, further inward. It's a quiet, precise kind of separation, not violent, not dramatic in the way we might imagine, just a boundary where the universe very calmly draws a line. Let's slow that down for a second. I want to make one thing clear, because it's easy to picture this wrong. The event horizon is not a wall that strikes you as you approach. It is not a surface that an object crashes into on arrival. It is a mathematical boundary in the geometry of space-time. And from the outside, nothing visibly marks its location. No fence post, no glowing ring, no sudden chill in the air. According to classical general relativity, an observer in free fall near a very massive black hole might not notice anything particularly unusual at the precise moment of crossing the horizon. At least not locally. That point matters, because the significance of the horizon is not mainly in what the crossing feels like in the instant it happens. Its significance lies in what the crossing means. Once across, there is no communication back. That is the definition, and that part is solid. Now, to be careful and honest, that picture of a smooth crossing belongs to classical general relativity. There are still open theoretical questions about what quantum physics may add to it, and no confirmed theory of quantum gravity yet exists to tell us the full story. So the smooth crossing picture is best understood as the prediction of classical GR. Well grounded, but not necessarily the final word. We'll come back to that later. For now, the important thing is simpler than it first sounds. The event horizon is not important because it is a physical barrier. It is important because it is a causal boundary, a line beyond which the rest of the universe can no longer receive word of what happens next. There's a related idea worth spending a little time with here. Not because you need to remember the name, but because it gives the horizon a more concrete shape. For a non-rotating black hole, General relativity describes the event horizon through what is called the Schwarzschild radius, named after Karl Schwarzschild, who derived one of the first exact solutions to Einstein's field equations. The Schwarzschild radius answers a simple question. If you took a given amount of mass and compressed it small enough, at what size would the escape velocity at its surface reach the speed of light? Compress a mass below that radius, and general relativity predicts a black hole forms, with its event horizon sitting at that radius. The key thing to carry forward is simple. The size of the event horizon scales directly with the mass of the black hole. More mass means a larger horizon, not a smaller one, a larger one. A black hole twice as massive has an event horizon twice as large. You do not need the name. Just keep the shape of the idea. Bigger mass, bigger horizon. Here is what many people find surprising when they first learn this. Because the event horizon is defined by a radius, by a mathematical boundary in space-time. There is nothing physically sitting there. No surface, no crust, no ground to crash into. A lot of people, quite naturally, imagine a black hole as something like a very dark, very dense planet, a solid ball you might fall onto if you drifted too close. That image is understandable. We are used to massive things being solid objects, but that is not quite right. One way to picture it, and this is only an analogy, not a precise description, is to imagine a whirlpool in a river. Far from the center, the current is gentle. You can swim in any direction, move freely, choose your path. But at a certain radius from the center of the whirlpool, the current moves faster than you can swim. That point is not marked by a physical line drawn in the water. There is no wall there. But cross it, and the water carries you inward regardless of how hard you try to move outward. The event horizon is like that. It is the point of no return, set by the geometry of space-time, not by any object placed there. There is no surface, no barrier you would see coming, only a threshold beyond which escape is no longer possible. Let's come at it from another angle, the black holes themselves. Black holes are broadly grouped into types, and the two we'll spend the most time with tonight are stellar mass black holes and supermassive black holes. The difference in scale between them is genuinely hard to picture. Stellar mass black holes are thought to form from the gravitational collapse of massive stars at the end of their lives. When a star considerably heavier than our Sun exhausts the nuclear fuel in its core, the fusion reactions that have been generating outward pressure and keeping it burning, the balance tips. Gravity, no longer held at bay by that outward pressure, gains the upper hand. Under the right conditions, the core collapses. What current models suggest can remain in those circumstances is a black hole. At the other end of the scale, observations of many large galaxies are consistent with the presence of supermassive black holes, millions to billions of times the mass of the Sun, at their centers, including our own Milky Way. The evidence for this has come from multiple independent lines of observation, built up over many decades. Both M87 star and SG are A star, the two black holes imaged by the Event Horizon Telescope, are supermassive black holes with masses estimated at millions to billions of times that of the Sun. Because the event horizon's size scales directly with mass, a supermassive black hole's horizon is correspondingly vast. And yet, at those distances, we still would not see the horizon itself. we would see only its effect on the light around it, its shadow. The underlying principle remains the same, regardless of scale. A boundary defined by gravity, beyond which light cannot return. Let's address something that naturally comes up here, because it is a fair question. How do we actually know any of this is real? If black holes do not emit light of their own, if we cannot take a direct photograph of the horizon itself, what is the actual evidence? We detect black holes through the way they affect everything around them, and from several independent directions. That evidence has grown genuinely strong. One compelling line of evidence comes from tracking the motions of stars near the center of our own galaxy. Over many years of careful observation, those stellar orbits have been measured with increasing precision, and their paths are consistent with the presence of an enormously massive, extraordinarily compact object at the galactic center. The best explanation we have is a supermassive black hole. Another line of evidence came from gravitational waves. LIGO detected ripples in space-time produced when two black holes spiraled together and merged. Not light, not radio signals, a physical ripple in the geometry of space-time itself. Since that first detection, LIGO and Virgo have confirmed multiple black hole merger events across a range of masses. And then there is the Event Horizon Telescope, a global network of radio observatories coordinated to study the immediate environment around black holes. By linking observatories spread across the Earth, it effectively functions like a single planet-sized telescope. In 2019, the EHT collaboration released the first image of a black hole shadow, the supermassive black hole M87 star. In 2022, it released a second image, this time of SGRA star, the supermassive black hole at the center of our own Milky Way. These images do not show the event horizon directly. Nothing from inside the horizon can reach us. What they show is the impression the horizon makes on the light around it, and that impression matches the theory with the precision that is quietly quite extraordinary. So here is where we are after this first part. The event horizon is a boundary in space-time, not a surface, not a wall, not a physical structure of any kind. Beyond it, according to general relativity, nothing escapes. Not light, not information, nothing. The horizon size is set by the mass of the black hole. Bigger mass, bigger horizon. Black holes come in a range of scales, from stellar mass to supermassive. We cannot see them directly, but stellar orbit measurements, gravitational wave detections, and radio telescope imaging all converge on a consistent and well-supported picture. And the theoretical grounding is strong. Roger Penrose was awarded the Nobel Prize in Physics in 2020 for work showing that black hole formation is a robust prediction of general relativity. There is something quietly grounded in that, I think. The event horizon is not a rough sketch. It is not a hand-waving hypothesis. It is one of the most carefully built and carefully tested ideas in modern physics. A boundary, a threshold, a one-way door in the structure of space-time, a place where the universe keeps its own counsel. And once that settles in, another question begins to rise. What happens to time near a boundary like that? Let's move very gently to that next part, when time slows. Time, it turns out, is not the same everywhere. And in the right place, in the right kind of quiet, it moves more slowly than you might ever imagine. That line is not a poem. It is not just a metaphor. As far as our best science can tell, it describes something real about the universe. And the remarkable thing is that this is not only a prediction written on a page somewhere. It has been measured with real clocks in laboratories on this planet. Let's take it one step at a time. Most of us grow up with a quiet assumption about time, so deep it barely registers as an assumption at all. Time feels steady, universal, the same for everyone. A second is a second. A minute is a minute. It feels too obvious to question. But that assumption turns out to be wrong. Not wrong in some exotic or philosophical sense. Wrong in a way that can be measured. Gravity causes time to run more slowly in regions of stronger gravitational fields. The stronger the gravity around you, the more slowly your clock ticks compared with a clock farther away from that pull. This is called gravitational time dilation, and it is not a small abstract curiosity. It has been confirmed by precision atomic clock measurements, and it quietly shapes the infrastructure of everyday life. Here is the gentle version of why. According to general relativity, a massive object does not simply pull things inward. It also curves the structure of space and time around it. Time itself is part of that structure, and in stronger gravitational fields, it runs at a different rate than it does in weaker ones. One way to picture it is to imagine two observers, one standing at the base of a very tall mountain and one standing at the summit. They are in the same gravitational field, but the person at the base is slightly deeper within it. A clock placed closer to a massive object ticks more slowly than one placed farther away. On Earth, that difference is extraordinarily small. You would never feel it. You would never notice it in ordinary life. But it is there, and it can be measured. Atomic clocks at different heights tick at measurably different rates, even across very small vertical distances here on Earth. That sentence is worth sitting with for a moment. Even across very small distances. Researchers at NIST measured a difference in clock rates between two optical clocks separated by a height of about 33 centimeters. Not 33 kilometers, not 33 meters, 33 centimeters. And the clocks disagreed. The one sitting slightly higher was in a marginally weaker gravitational field, and so it ran marginally faster than the one slightly lower. Exactly as general relativity predicted. It is the kind of result that is easy to read past, but it is extraordinary. The very tool we use to track the passage of time does not behave the same way everywhere. Gravity bends it, gently on Earth, but measurably, precisely. Now, let's bring that back to the main thread. If gravity already makes a measurable difference across 33 centimeters on Earth, a planet with relatively modest gravity by the standards of the universe, what happens in far stronger gravitational fields? The stronger the gravity, the more pronounced the time dilation becomes. You do not have to go all the way to a black hole to find a practical example of this in action. GPS satellites, the system we rely on for everyday navigation, require ongoing corrections for relativistic effects. Their clocks are affected both by gravity and by their motion in orbit. Without those corrections, errors would accumulate quickly enough to make the system unusable. Every time a navigation system quietly finds a location, it is also quietly confirming Einstein's predictions about time. The corrections work, and because they work, the physics beneath them works too. So this is no longer only theory. It is engineering. It is infrastructure. It is part of ordinary life. Now, gently, let's zoom out. We have established that time runs more slowly in stronger gravitational fields, measured on Earth, confirmed in orbit. In familiar settings, the effect is small. Near a black hole, it becomes far more extreme. General relativity predicts that, from the point of view of a distant observer, time dilation near a black hole's event horizon becomes extraordinarily large, approaching, in theory, an infinite slowdown right at the horizon itself. That phrasing matters from the point of view of a distant observer. This is a prediction about what someone far away would calculate or appear to see when watching an object fall toward the horizon from outside. From that distant vantage point, the falling object would appear to slow more and more as it approached the boundary. Its clock would seem to tick more and more slowly. In that description, the object seems never quite to reach the horizon at all. That image, something appearing to freeze at the edge, never fully arriving as seen from far away, is one of the strangest predictions in physics, and it grows from the same principle as the NIST clocks. Only now we are following that principle into a regime far beyond anything a laboratory on Earth can reproduce. There is something else happening alongside this slowing of time, something closely connected to it, and something we can also observe. Light emitted from a region of strong gravity appears shifted toward longer, redder wavelengths when received by a distant observer. This is called gravitational redshift. Here is the simple version. A photon climbing out of a gravitational well loses energy along the way. It still travels at the speed of light, but its energy is reduced. Lower energy means longer wavelength, and longer wavelength means the light is shifted toward the red end of the spectrum. So light sent from near a very massive object arrives, looking different, stretched, reddened, changed by the long climb outward. The deeper the gravitational well, the more pronounced that effect becomes. And like time dilation, gravitational redshift is not only theory, it has been observed. In 2018, instruments working with a very large telescope measured the gravitational redshift of the star S2 as it passed near SGRA star, the supermassive black hole at the center of our galaxy. S2 does not cross the event horizon, but at its closest approach, it moved through a strong enough gravitational field for this effect to be measured clearly. And the results match the predictions of general relativity. That matters not because it shows us the horizon directly, but because it tests the theory in the strong gravitational field around a supermassive black hole. And now, the deeper connection. Time dilation and gravitational redshift are not just two separate oddities that happen to appear in the same place. They are two windows onto the same underlying geometry. Gravity slows time in stronger gravitational fields. Gravity also redshifts light climbing out of those fields. And the link between them is direct. A clock that runs more slowly produces signals at a lower frequency, and lower frequency means longer wavelength. Slow the clock, and you also stretch the light. So what would the light look like coming from an object falling toward a black hole's event horizon? From far away, it too would appear increasingly stretched, more redshifted, dimmer, fainter, more drawn out in time. General relativity predicts that to a distant observer, an object falling toward the event horizon would appear to slow, redden, and gradually fade from view. not vanish in a flash, not explode, just dim, more and more gently, into the dark. To that distant observer, it would never quite be seen crossing the horizon at all. That image, a slow fading at the edge of one of the most absolute boundaries in the universe, is one of the quietest and strangest ideas in science. If your mind drifts a little here, that is perfectly fine. But let's pause and draw an important line. Everything in this chapter, the slowing of time, the stretching of light, the progressive dimming seen from far away, comes from general relativity applied near a black hole. And general relativity is one of the most carefully tested theories in science. Atomic clocks at different heights tick at different rates. GPS depends on relativistic corrections. The gravitational redshift of S2 near SGR A star matched the prediction. These confirmations matter. They give us strong reason to trust the theory. But we should still be honest about where direct confirmation ends and confident extrapolation begins. No direct observation has been made of the interior of a black hole, and the extreme slowdown predicted right at the event horizon has not been directly measured at that location. We are extending a rigorously tested theory into a regime where no direct measurement has yet been made. General relativity gives us very strong grounds for doing that, but at that point, it remains a prediction, carefully labeled as one. That distinction matters. For now, let's close this part simply. Time is not fixed. Gravity slows it. Stronger gravity slows it more. Near a black hole's event horizon, that slowing becomes, according to general relativity, extreme beyond anything we encounter in ordinary life. And alongside it, light climbing out of strong gravity is stretched and reddened, its energy spent in the long climb away. These two effects are woven into the geometry of space-time itself, in the same region where we found, in the last chapter, that quiet and precise boundary, the horizon we described before, not a wall, but a threshold in the structure of space-time, also turns out to be a place where time, as we normally understand it, begins to behave in a profoundly unfamiliar way. And from here, there is only one gentle direction left to go. If gravity can slow time and stretch light, what else can it do to light itself? That is where we will go next. For now, just rest here for a moment. Let this settle quietly. When light bends, light has always seemed like the straightest, most dependable thing in the universe. And yet, even light, it seems, can be gently persuaded to bend. We tend to think of light as the ultimate traveler, fast beyond imagining, straight by nature, unbothered by obstacles in a way that almost nothing else can match. When you switch on a lamp, light does not wander or hesitate. It simply goes, in a direct line, at the fastest speed anything in the universe can travel. That image, straight, dependable, unwavering, is accurate in most of the universe, most of the time. But near a very massive object, the story changes. General relativity predicts that light does not travel in a straight line near a massive object. Its path curves because the massive object has curved the very space-time through which the light is traveling. Light follows the geometry of space-time faithfully. And if that geometry is curved, the path of light curves with it. This is not light being pushed or pulled in any mechanical sense. There is no hand reaching out to deflect it. The geometry itself has changed, and light, doing exactly what light always does, follows that changed geometry. The result, to an outside observer, is a curved path. This effect has a name. It is called gravitational lensing, and it is not a fringe prediction or a theoretical curiosity. It has been observed, confirmed, and documented many times from many independent directions. One of the earliest and most famous confirmations came during a solar eclipse. Starlight passing close to the edge of the sun, as seen from Earth during a total eclipse, was found to be shifted from its expected position, bent by the sun's gravity, just as general relativity had predicted. It is, in retrospect, a wonderfully direct result. The sun's gravity bent the path of light from distant stars just enough to be detected. A subtle shift, a small arc in a photon's journey across immense distance, and it matched the theory. Since then, gravitational lensing has been observed again and again in many different forms. A background astronomical object can appear brighter, stretched into arcs, or split into multiple images, depending on the alignment between the light source, the lensing mass, and the observer. If you want a simple everyday comparison, think for a moment of the way a glass of water can distort the appearance of something behind it, stretching it, reshaping it, making it appear displaced. Gravitational lensing works on an incomparably larger scale, with mass curving space-time rather than glass bending light. But the visual quality of strange, beautiful distortion is not entirely unlike that everyday experience. The Hubble Space Telescope has documented many striking examples of this. Arcs of light, distorted background galaxies, and Einstein rings, where a distant source appears as a nearly perfect circle because of precise alignment with a foreground mass. These are some of the clearest visual reminders that gravity does not only pull on matter, it also shapes the paths along which light itself can travel. And near a black hole, that shaping becomes far more extreme. We are no longer talking about a slight shift in the apparent position of a distant star. We are talking about light paths so strongly curved that they can be folded back sharply, rerouted in ways that have no real parallel in the weaker gravity we know elsewhere. In the strong gravitational field close to a black hole, light can be redirected back toward the black hole rather than escaping outward, not merely diverted slightly, not just nudged off course, but turned back, captured, prevented from reaching the wider universe. This is the mechanism behind the black hole shadow. The dark central region visible in the Event Horizon Telescope images is not simply an empty hole in the picture. It is the region where the black hole's gravity has captured incoming light so that none of that light reaches the observer. The darkness is not an absence of things. It is an absence of light that can carry information outward. Let's stay with that for a moment, because this is where the images become even more interesting than they first appear. When people first see the EHT images, they often focus on the darkness at the center. But the bright ring around that darkness is just as remarkable. It is not simply a glowing outline painted onto the edge of the black hole. Accreting matter contributes to the brightness, yes, but the ring is also something more striking than that. The bright ring seen in the EHT image is light that has been dramatically bent by the black hole's gravity and redirected toward Earth. Light that in some cases began in a very different direction, curved by the extreme geometry of space-time, and eventually arriving at our telescopes. That is worth holding in the mind for a moment. Not simply nearby matter glowing in place, but light from many directions, bent and gathered, rerouted by gravity into a visible structure. Lensing near a black hole can cause an observer to receive light that originated from regions behind and around the black hole, bent into rings and arcs by the extreme gravity. And so, the picture near a black hole is not simply one of darkness swallowing everything. It is a folding, a rearranging, a place where light from across the universe can be curved into unexpected paths and arrive from unexpected directions. An observer situated closer to a black hole would, according to general relativity, see the surrounding sky profoundly distorted. Light from many different directions would be bent, warped, and redirected around them. The sky there would bear little resemblance to the sky we know. It would carry light that had traveled long, looping paths through a region of extreme curvature. And that brings us to a particularly striking part of the geometry. There is a specific region around a black hole where the bending of light becomes so strong that photons can, in principle, travel in circular paths. This region is called the photon sphere. The photon sphere lies outside the event horizon, but still deep within the region of extreme gravitational curvature. For a non-rotating black hole described by general relativity, it sits at a distance from the center equal to 1.5 times the Schwarzschild radius. That places it outside the horizon, but very much within the black hole's gravitational grip. Let's slow that down for a second. The event horizon is the boundary from which nothing escapes. The photon sphere sits outside that boundary. A photon at the photon sphere has not yet crossed the final threshold, but it is in a region where gravity is strong enough to hold light in a circular path, not spiraling gently like an ordinary orbit, not resting safely, but circling in principle, because the geometry allows it. As a thought experiment, if you could somehow be positioned at the photon sphere and look sideways, not inward, not outward, but along the direction of those circular paths, you would, in principle, be looking at the back of your own head. Light could complete a full loop around the black hole and return to its starting point. That sounds almost like science fiction, but it is simply what the geometry implies. And yet those circular photon paths are unstable. That part matters. A photon at the photon sphere is not safely parked there. The smallest deviation from the circular path and it will begin moving one way or the other, outward, eventually escaping, or inward, falling past the event horizon. There is no stable middle ground. The photon sphere is a kind of geometric knife edge, a place where balance is possible in principle, but inherently precarious. In practice, photons passing through this region skim along those nearly circular paths only briefly, before eventually departing one way or the other. And photons arriving from across the universe, passing through this region at just the right angle, can have their paths dramatically altered, curved, partially looped, redirected. That altered light contributes to the extraordinary visual structure the EHT has imaged around both M87 star and SG, our A star. Now, there's an even more refined prediction that grows out of this same geometry. It is called the photon ring. The idea is elegant. If some light completes one or more full loops around the black hole before finally reaching the observer, then that light should contribute to a very narrow, bright ring nested within the broader emission structure. Each additional loop a photon completes would contribute to an even finer ring inside the previous one, a delicate stack of ever more compressed rings. This predicted photon ring is especially important because its geometry is expected to depend mostly on the mass and spin of the black hole itself, rather than on the messy details of the hot gas around it. That makes it, in principle, one of the cleanest signatures of general relativity in the strong field regime. But here, again, it helps to be precise. The photon ring has not yet been directly resolved as a distinct feature in current EHT images. It remains a theoretical prediction, well grounded in the physics, consistent with what has been observed, but not yet isolated cleanly from the broader emission ring. Resolving it is a goal for future observations, likely requiring even more powerful arrays and possibly longer baselines extending beyond Earth. That, too, is part of what makes science beautiful. Knowing what has been seen, being honest about what has not yet been separated out, and then building the next instrument to go looking. Let's pause and hold the two EHT images side by side in the mind. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole shadow, M87 star, the supermassive black hole at the center of the galaxy Messier 87. The image showed a bright, roughly circular ring of emission surrounding a darker central region. In 2022, the EHT released its second image, SGRA star, the supermassive black hole at the center of our own Milky Way. That image, too, showed a bright ring surrounding a dark shadow region. Two black holes, different masses, different galaxies, different distances, and yet both images were consistent with the same basic structure predicted by general relativity. That is a remarkable thing to sit with quietly. The EHT achieved this by linking radio observatories spread across the Earth, effectively creating a planet-sized telescope. And both images, produced years apart, aimed at completely different objects in completely different parts of the universe, revealed the same fundamental pattern. A bright ring, a dark center, and the visible signature of light moving through intensely curved space-time. So let's close this chapter simply. Light bends in strong gravity, not because anything pushes it, but because space-time itself is curved, and light follows that curvature. This has been confirmed across many kinds of observation, from starlight near the Sun to modern radio imaging of black holes. Near a black hole, that bending becomes extreme. Light can be turned back. In the photon sphere, outside the event horizon, but deep in the region of extreme gravity, photons can travel in unstable circular paths. Those paths are precarious, and light passing through that region can have its direction altered dramatically, contributing to the visual structure captured in the EHT images. The finer photon ring remains a prediction not yet separately resolved, but the broader bright ring dark shadow structure has now been seen around two very different black holes. There is something almost meditative, I think, about light near a black hole. A photon may begin from some distant source, curve around a black hole, loop through deep gravity, and continue on across the universe until it arrives at a telescope on Earth, carrying, in its altered path, a record of the geometry it traveled through. And once you start to picture light that way, another question begins to open. What does this whole journey look like from two different points of view? from far away, and from the perspective of something falling inward. That is where we'll go next. For now, let the light settle, and when you're ready, we'll move on together. Two viewpoints, the same journey seen from two different places, can look like two entirely different stories, and both of them can be true at the same time. There is a question that comes up naturally after everything we've covered so far. We have talked about the event horizon as a boundary, a threshold in space-time beyond which nothing escapes. We have talked about time slowing near it, light bending around it, a shadow forming in its wake, and all of that so far has mostly been described from a kind of outside perspective, the view of someone watching from a comfortable distance, far from the black hole itself. But what about the other point of view? What about an observer who is not watching from far away, but is instead falling inward? This is where the story becomes especially strange. In general relativity, these two perspectives are not interchangeable. They do not describe the same sequence of events in exactly the same way. The difference between what a distant observer would describe and what an infalling observer would describe arises from their different reference frames in space-time. And that last part matters. We are not going to say that one observer is right and the other is wrong. Both descriptions come from the same theory. Both follow from the same mathematics. They are two accounts of the same physical situation, given from two different vantage points, and general relativity makes room for both. Let's take them one at a time. We'll begin with the distant observer, because we have already been building that picture. Across the last two chapters, we have spent time describing what a distant observer would see and measure when watching an object fall toward a black hole. That picture is built from the same two effects we have already followed carefully: time dilation and gravitational redshift. According to general relativity, time dilation near a black hole's event horizon becomes extreme, approaching, in theory, an infinite slowdown right at the horizon itself, as seen from far away. So a distant observer watching an object fall toward a black hole would see it appear to slow down progressively, slower and slower, more and more drawn out in time. And from that outside perspective, the object would never quite seem to cross the horizon at all. General relativity also predicts that as the object approaches the horizon, the light it emits would be received by the distant observer as increasingly redshifted, stretched toward longer and longer wavelengths, growing fainter and dimmer. These two effects work together. The distant observer would watch the infalling object slow, redden and fade, appearing to hang at the edge of the horizon, until eventually its light becomes too stretched and too faint to detect. That picture is not a mistake. It is not an illusion in the sense of being false. It is a real prediction about what that distant observer's instruments would record. Let's slow that down for a moment, because there is an important subtlety here. The distant observer sees the object slow, redden and fade. The light from the falling object takes longer and longer to reach them as the object gets closer to the horizon. And eventually, the outward stream of photons becomes so thinned out, so stretched and so dim that the object becomes practically invisible. From that observer's point of view, the object never quite reaches the horizon. But this does not mean the object is physically halted there. like something suspended in space at the edge. This apparent freezing is what physicists describe as a coordinate effect. It reflects the way information from the falling object reaches the distant observer. It does not mean the object itself has stopped in any absolute sense. That distinction matters. In general relativity, different coordinate systems can describe the same physical situation in different ways. What appears as an infinitely slow approach in one coordinate language can appear smooth and finite in another. Both descriptions are mathematically valid within the theory. The difference lies in how the space-time is being described, not in a contradiction in the underlying physics. This is one of those places where everyday intuition starts to strain a little. We are used to thinking there should be one single universal description of what happened. General relativity does not always work that way. It tells us that both accounts can be valid descriptions of the same situation from different reference frames. Neither observer is mistaken. They are speaking from different places within the same geometry. Now let's turn to the other perspective, the infalling observer. And here, the story changes character quite noticeably. According to classical general relativity, an observer in free fall toward a black hole would not, locally, experience anything especially dramatic at the exact moment of crossing the event horizon. That is one of the more surprising predictions in all of physics, and it is worth unpacking slowly. The reason comes from one of the central ideas in general relativity, the equivalence principle. Very roughly, this principle tells us that free fall in a gravitational field can, locally, feel like floating freely in empty space. As a familiar example, an astronaut inside a spacecraft that is freely falling near Earth, not firing rockets, simply falling, floats weightlessly. Locally, their environment does not announce gravity in the way everyday life makes us expect. Extended to a freely falling observer near a black hole, classical general relativity predicts something similar. At the moment of crossing the horizon itself, there is no wall to strike, no surface to crash into, no sudden physical marker announcing, "You are here." The event horizon is not a material thing. It is a boundary in the geometry of space-time. And in the frame of the freely falling observer, that local geometry at the crossing can be unremarkable. It is important to hold this carefully. This is the prediction of classical general relativity. It is grounded in a very well-tested theory, but it is still a prediction applied to a regime that no human observer has ever reached, and no instrument has directly measured from the inside. Now here is the part many people find most striking when they place the two pictures side by side. The distant observer sees the object freeze and fade, never quite crossing. The infalling observer crosses without a dramatic local signal. At first glance, those accounts can sound completely incompatible, and yet both arise from the same theory. Both follow from general relativity, applied from different reference frames in space-time. Neither one is wrong. What appears to take infinite time in the distant observer's coordinates appears smooth and finite in the infalling observer's own frame. The same space-time geometry, described in two different ways, produces two accounts that look, on the surface, like two different stories, but underneath, they belong to the same structure. There is a familiar hint of this already in special relativity. Two observers moving differently can validly disagree about the timing of distant events, General relativity extends that kind of freedom much further into deeply curved space-time. What remains shared is not the surface wording of events, but the deeper physical geometry beneath them. Let's add one more layer here, because it makes the infalling picture more concrete. Tidal forces near the event horizon depend strongly on the mass of the black hole. That matters. Near a stellar mass black hole, the horizon is relatively compact, and the difference in gravitational pull across an extended body can become very large in the region approaching the horizon. Near a supermassive black hole, the horizon is vastly larger, and the tidal forces at the horizon can be much gentler by comparison. So the idea of a locally unremarkable crossing is not something we should imagine in exactly the same way for every black hole. It is especially applicable to a sufficiently massive black hole, where the local stretching forces at the horizon itself may be modest. For a smaller black hole, the infalling observer would still be dealing with much more severe tidal effects in the surrounding region. So even here, the details depend on the black hole in question, and that is worth remembering. Now let's bring in one more thread, because it completes the picture. According to general relativity, once an object crosses the event horizon, it cannot return to the outside universe. The structure of space-time beyond the horizon allows only directions that lead further inward. That is true whether the crossing feels dramatic or not. So in the infalling observer's own frame, the moment of crossing may not announce itself with a violent local event, but the geometry of their future has changed completely. From that point onward, every available path leads deeper inward. No outward route remains, no light signal they send, no radio transmission, no final message. Nothing they do can restore communication with the outside universe again. There is something quietly significant in that. The boundary is not marked by a wall. It is not announced by a crash or a jolt. And yet, in the structure of what is possible from that moment forward, everything has changed. The event horizon is the threshold beyond which events can never inform the outside universe. From the infalling observer's perspective, they have entered a region from which outward communication is no longer geometrically possible. The universe they came from has, in a precise sense, become unreachable. Now, this is also the point where it becomes especially important to be honest about the limits of what we know. Everything we have described in this chapter, both the distant observer's picture and the infalling observer's picture, comes from classical general relativity. And classical general relativity is a spectacularly successful theory. It has been tested again and again. It predicts black holes as robust outcomes of gravitational collapse. And that matters. But classical general relativity does not include quantum mechanics. And near black holes, especially in the most extreme conditions, many physicists expect quantum effects to matter in ways that could alter this picture. General relativity is widely expected to break down at the most extreme conditions near a singularity, and some open questions suggest that a complete theory of quantum gravity may eventually revise aspects of how we think about horizons as well. At the moment, no confirmed theory of quantum gravity exists to tell us the full story, so there is a limit to how far honesty allows us to go. Within classical general relativity, these two viewpoints are well defined. Beyond that, the picture becomes more open. The information paradox, The question of what ultimately happens to information that falls into a black hole sits right at the center of that uncertainty, and it touches directly on the deeper relationship between these two observers and the full story neither of them can yet tell alone. These are not tiny footnotes. They are real, central, unresolved questions, and they deserve their own space. That is where we will go in the next chapter. But for now, within the framework of classical general relativity, the picture is this. A distant observer sees time slow, light redden, and an infalling object fade gradually at the edge of the horizon, appearing never quite to cross. An infalling observer, in the framework of classical GR, crosses without a dramatic local signal, but enters a region of space-time from which no return and no outward communication is possible. Both perspectives arise from different reference frames. Both are valid descriptions within the theory. Neither one is wrong. They are two faces of the same geometry, seen from two different positions. And there is something quietly grounding in that. Once you let it settle, the universe does not offer every observer the same description. It offers each observer a description that is valid from where they stand. The distant observer, far away, watching through instruments, receives one account. The infalling observer, crossing the threshold, receives another. And the theory that contains both accounts is the same theory. One framework, two views. You do not need to hold on to every detail of that. What matters most is simply this. In the physics of black holes, perspective is not decorative. It is fundamental. Where you are and how you are moving shapes what the universe shows you. And once that settles in, the next question becomes unavoidable. How far can we really trust this picture? Where does confident prediction end and real uncertainty begin? That is where we will go next. For now, let chapter 4 rest, and when you are ready, we will meet chapter 5 together. What we can say, and what we can't yet. There is a kind of peace that comes from knowing exactly how far our understanding reaches, and from sitting quietly with everything that lies just beyond it. That line carries something I mean quite genuinely tonight. In science and in life, there is a particular kind of discomfort that comes from not knowing, from standing at the edge of what is understood and looking out at territory that has not yet been mapped. We often feel that uncertainty as a lack, as something to be fixed, something to be resolved, something uncomfortable to sit with. But there is another way to hold it. Knowing precisely where your knowledge ends is not a failure. It is one of the most rigorous things a mind can do. It means you have followed your understanding all the way to its outer edge. And it means you have been careful enough not to step beyond it and pretend you are still on solid ground. In this final factual chapter, that is exactly what we are going to do. We are going to walk carefully to the edge of what is genuinely known about the event horizon, what has been observed, confirmed, and established, and then stand there honestly. Look at what lies beyond the reach of current knowledge and name it clearly for what it is. Let's take it one step at a time. Here is what we can say. Let's begin with the observational foundation, the things that do not rest on theory alone, but on instruments, measurements, and results that have been independently checked and confirmed. LIGO detected gravitational waves from merging black holes, physical ripples in the geometry of space-time, produced by some of the most energetic events in the observable universe. Multiple black hole merger events have since been confirmed by LIGO and Virgo, identifying stellar mass black holes across a range of masses. Together, these detections provide strong, direct physical evidence for black holes as astrophysical objects, and that evidence does not depend on light. It opened a new observational window on the universe entirely. Observations of stellar orbits near the center of our own galaxy have also, over many years of measurement, pointed to the presence of an enormously massive and extraordinarily compact object at the galactic center. The gravity instrument, working with the Very Large Telescope, measured those orbits around SGURA star with extraordinary precision, confirming the presence of something immense packed into a region too small and too dense to be explained by any known alternative under current physics. That same line of work also tested general relativity in the strong gravitational field around a supermassive black hole, and the gravitational redshift of the star S2 near SGRA star was found to be consistent with the theory's predictions. Then there are the Event Horizon Telescope images. In 2019, the EHT collaboration released the first image of a black hole shadow, M87 star. The image showed a bright ring of emission surrounding a darker central shadow region. In 2022, the EHT released a second image, SGRA star, at the center of our own Milky Way, which also showed a bright ring and a dark shadow consistent with the same underlying structure. Together, these images represent some of the most direct observational evidence yet obtained for the predictions of general relativity in the strong gravity regime. So this is the observational foundation. It is real, it is independently confirmed, and it is not in serious scientific dispute. Now let's move to what we can say with confidence on the theoretical side, clearly labeled as theory, but theory of a very well-tested kind. General relativity predicts that the event horizon marks the boundary from which nothing, not even light, can escape. Once crossed, no object can return to the outside universe. No event inside can ever inform the outside. Events beyond the horizon are permanently beyond the reach of any outside observer. Gravity slows time. That has been confirmed in laboratories. Atomic clocks at different heights run at measurably different rates, even across distances as small as 33 centimeters. GPS satellites carry live relativistic corrections every day, and those corrections work. General relativity predicts that time dilation near the event horizon becomes extreme, approaching, in theory, an infinite slowdown right at the horizon itself, as calculated from far away. Light climbing out of strong gravity is redshifted. That has also been measured. It has been observed near a supermassive black hole, in a way consistent with general relativity's predictions. Light bends in curved spacetime. That has been confirmed from solar eclipse measurements to modern telescope imaging. Near a black hole, that bending becomes extreme enough to redirect light back entirely. A photon sphere exists, where photons can travel in unstable circular paths, outside the event horizon, but deep within the region of extreme curvature. Those paths are unstable. Photons passing through that region can have their trajectories altered dramatically, and the two observer perspectives, distant and infalling, are both valid within general relativity, arising from different reference frames in space-time. What appears as infinite slowdown in one coordinate system appears smooth and finite in another. Both descriptions are legitimate within the theory. Roger Penrose was awarded the Nobel Prize in Physics in 2020 for theoretical work showing that black holes and the event horizons that define them are robust predictions of general relativity. That is a substantial body of established knowledge, and it is worth appreciating how much of it exists and how carefully it has been built. Now we come to the other side. Here is what we cannot say, at least not yet. This is the honest edge. No direct observation has ever been made of the interior of a black hole. And under general relativity, no such observation can ever be made from the outside. No signal can escape from beyond the event horizon to reach an outside observer. No light, no radio wave, no message of any kind. There is no telescope, no instrument, no future improvement in resolution that can give an outside observer a direct view of what lies inside. That is not merely a technological limitation. It is built into the physics itself. The event horizon is defined by exactly this impossibility. We cannot observe beyond it from outside. Not because our tools are still too weak, but because information cannot make the outward journey at all. That is a clean and honest limit, worth sitting with rather than rushing past. What happens to matter and energy beyond the event horizon can be described mathematically within general relativity, but none of those descriptions can be verified directly by any outside observer. The mathematics gives us a framework for thinking about the interior, but by the nature of the horizon itself, that framework is permanently insulated from direct outside confirmation. And then there is a second limit, one that comes not from observation, but from the theory itself. The singularity predicted at the center of a black hole marks the point where general relativity's own equations break down, where the theory stops making reliable predictions. That is not an external criticism of general relativity. It is something the theory itself implies when followed honestly to its extreme conclusions. In that sense, it is a sign of an honest theory. Its limits are written into its own results. General relativity is widely expected to require modification at the most extreme conditions near a singularity, where quantum effects are expected to matter in ways the theory cannot account for on its own. But no confirmed theory of quantum gravity yet exists. We do not yet have a single consistent framework that fully unifies general relativity and quantum mechanics into one complete description of nature at these extremes. What that means in practice is simple. Any description of what physically occurs at or near a singularity remains, at present, beyond the reach of confirmed physics. General relativity gives us the best framework we have. But in that regime, it cannot be taken as the final or complete account. We genuinely do not know, and saying so is not weakness, it is precision. Let's come at it from one more angle, because the limits of our knowledge do not stop at the singularity. They also reach up to the horizon itself once quantum effects enter the picture. Classical general relativity predicts that a freely falling observer would experience no dramatic local signal at the moment of crossing the event horizon. That is the classical answer. But classical general relativity does not include quantum mechanics, and no confirmed theory of quantum gravity yet exists to tell us what a complete description of that crossing would look like in a theory that includes both. There are active areas of theoretical research exploring whether quantum effects could significantly alter the picture near the horizon. These are real questions, carefully debated, seriously studied, not resolved. What matters for us tonight is simply this: the question of what happens at the horizon in a full theory that includes both gravity and quantum mechanics remains open. The classical answer is well defined. The complete answer from a theory we do not yet have is not. And there is one open question that deserves its own careful moment, because it sits at the intersection of nearly everything we have covered tonight. It is called the information paradox. This is one of the central unresolved questions in theoretical physics. Here is a gentle version of why it matters. According to quantum mechanics as we currently understand it, physical systems evolve in ways that are, in principle, reversible. The complete description of a system at one moment contains, in principle, enough information to reconstruct its description at another. Information in that framework is preserved, but once something crosses the event horizon, nothing about it, no signal, no information, no trace, can escape back to the outside universe under general relativity. What happens beyond the horizon is permanently inaccessible to outside observers. And that creates a deep tension. If information is preserved in quantum mechanics, but seems to disappear beyond the horizon under general relativity, then two of our most successful frameworks appear to be pointing in different directions. That is exactly what makes the paradox so important. It remains unresolved. Many proposed resolutions exist, but none has achieved scientific consensus. And the answer, when it comes, may require a fundamentally new understanding of the relationship between space-time, gravity, and information itself. That is the frontier, not a tidy edge, not a cleanly fenced border, a genuinely open question, and one of the most important ones in modern physics. So let's close this chapter clearly. What we can say: gravitational wave detections have confirmed black hole mergers. Stellar orbit measurements confirm an extraordinarily massive compact object at the center of our galaxy. Two black hole shadows have been imaged by the Event Horizon Telescope, consistent with general relativity's predictions. Gravitational time dilation is confirmed by laboratory clocks. Gravitational redshift has been measured near a supermassive black hole. Light bending by gravity is confirmed across a wide range of observations. The event horizon is a well-grounded prediction of general relativity, a one-way boundary in space-time from which nothing escapes and nothing communicates outward. This prediction is robust. It emerges naturally from the theory under realistic conditions. And what we cannot say, no direct observation of anything inside a black hole has been made, or can be made from outside. General relativity's own equations break down at the singularity. No confirmed theory of quantum gravity exists to describe what happens there, or to tell us what a complete description of the horizon would look like in a full theory. And the information paradox remains genuinely open. The distance between what we can say and what we cannot is not a failure of science. It is science being precise about itself. The known is genuinely extraordinary, and the unknown is genuinely, honestly still unknown. Both of those things are worth holding quietly, and from here, a final thread remains. If the event horizon marks the limit of what can return, What becomes of information that falls across it? And what might that question tell us about the deepest nature of space-time itself? That is the path Episode 3 will follow. We will approach it the same way we approached everything tonight, carefully, without the overclaiming, following the evidence as far as it reaches, and naming the limits clearly where they exist. For now, let this chapter settle. You have carried a great deal of careful thought with you tonight. The boundary of the known is a real place, and tonight you have reached it. The wind down is just ahead, and it is a gentle one. Rest inside the quiet. You've traveled a long way tonight, not in miles, but in the slow, unhurried way that the universe itself moves. And now it is time to simply rest inside all of it. You can let everything go now, all of it. The ideas, the questions, the careful following of one thought into the next. You do not need to hold on to any of it. Whatever settled in, settled in. Whatever drifted past, drifted past. Either way is fine. Either way is exactly right. This is the part of the evening where we stop explaining, stop understanding, and simply breathe. So let's do that first. Just once, slowly. Breathe in, and let whatever you are holding loosen a little. Breathe out, and feel the weight of the day move a little farther away from you. Good. There is no hurry from here. Imagine very gently that you are somewhere quiet. Not the cold, dramatic quiet of empty space. Not that. Something warmer than that. Something like the quiet of a very still night, when the air is soft and the darkness feels friendly rather than empty. The kind of quiet where you can hear your own breathing, and it sounds like the most natural thing in the world. You are resting there. The sky above you is full, not crowded, not overwhelming, just full. The way a sky can be when you are far from the lights of ordinary life, when the stars seem less like distant objects and more like companions. They have always been there. They will be there long after tonight. And there is something comforting in that, if you let yourself feel it. And out beyond all of that, beyond the familiar shapes and the nearest lights, somewhere in all that quiet depth is the place we travel to tonight. You do not need to look for it. You do not need to find it. It is enough to simply know that it is there. Picture yourself, very slowly, drifting outward. Not falling, not rushing, just drifting. The way a leaf drifts down a very still stream, without effort, without direction, carried by something gentle and enormous that does not need your help to move. The light around you grows quieter as you drift. The colors soften. What was bright becomes golden. What was golden becomes amber. What was amber becomes a deep, warm rose, and then softer still, a quiet red, like the last light in a room when someone turns the lamp low before leaving you to sleep. You are not going anywhere dangerous. You are not really going anywhere at all. You are simply watching the light change around you, the way light always changes when you move towards something large and still and ancient. Not darker exactly, just deeper. Let your body sink a little further into wherever you are resting right now. Your shoulders, your hands, the small of your back. Let the surface beneath you hold a little more of your weight. You do not have to carry yourself quite so much tonight. Somewhere ahead, in your imagination, there is a boundary. You do not have to cross it. You do not even have to approach it closely. It is enough to know it is there. That edge where one kind of knowing ends and another kind of quiet begins. a soft threshold where the familiar rules of things begin to loosen, gently, like a knot that does not need to be forced, only allowed to ease open on its own. It is not frightening. That may be the thing most worth carrying into sleep. It is not frightening at all. It is simply still. Think of all the things you let go of tonight, one by one. Not dramatically, just naturally. The busyness of the day, the list of things left undone, the quiet anxieties that hum in the background when there is nothing else to listen to. Those things did not follow you all the way out here. They stayed behind, somewhere back where the lights are busy and the hours feel short. Out here, in this imagined quiet, time does not press against you in the same way. Time, out here, has more room, and you have more room inside it. Let that feeling stay with you, not as an idea to hold carefully, just as a warmth, a loosening, a sense that the night is longer, gentler, and more patient than you sometimes remember it being. Your breathing has slowed a little now, I think, without you having to ask it to. That is good. That is your body remembering what it already knows, that sleep is not something you have to chase or earn or prepare for perfectly. It comes on its own when you stop insisting on being somewhere else. And you do not have to be anywhere else tonight. You are here. The night is quiet. The universe is unimaginably large, and somehow that largeness can feel like a comfort rather than a pressure. Because in something that enormous, your rest, this small, ordinary rest, here and now, matters not less. It matters more. It is exactly as real as anything out there, maybe more real in a way, because you can feel it now, if you like. The weight of rest, the softness of a mind that has thought carefully for a while and is now, gently, releasing its grip. Let the images from tonight come back to you slowly, if they want to. Not as lessons to review, not as things to remember correctly, just as pictures drifting through, the way images move through the space between waking and sleep. A boundary in the dark, a ring of light around a deep stillness, a clock somewhere ticking more slowly than a clock somewhere else. The universe keeping its own quiet, unhurried rhythm. Light that bends, light that curves, light that travels long, looping paths through patient, folded space before arriving, finally, somewhere it can rest. Two travelers, one watching from far away, one falling inward, each seeing something true, each seeing something different, each held within the same enormous framework that holds everything. And a question at the edge of all of it, a question nobody has answered yet. An open door at the end of a long corridor, lit softly from somewhere beyond it. Not harshly, not urgently, just enough to remind you that the unknown is not always something to fear. Sometimes it is simply something unfinished, and unfinished is fine. Unknown is fine. Unknown is, in its own way, a kind of rest. It means there is still more to come. Let your eyes be heavy, if they are. Let your thoughts grow loose and unhurried, the way thoughts do when sleep is close, when they stop having to mean anything in particular and start floating softly, like dust in a late beam of light. You are not far now. The part of you that keeps watch, the part that checks whether things are okay, whether you forgot something, whether you are doing rest correctly. Let that part take the night off. Everything is okay. You have not forgotten anything important, and rest does not need to be done correctly. It only needs to be allowed. So allow it. Somewhere out in the deep quiet of the universe, a boundary sits, patient, still, unhurried, and the light that surrounds it bends gently in the dark, traveling its long curved path across distances that have no names in ordinary language. And here, much closer, in whatever small and warm and ordinary place you find yourself tonight, you are resting. Both things are true at once, the enormous and the intimate, the ancient and the immediate, the question with no answer yet, and the simple fact of breath and blanket, and the particular darkness behind closed eyes, a darkness nothing like the darkness of space, warmer than that, closer than that, more your own. You have done enough tonight. You thought carefully. You followed the thread as far as it went. You stood at the honest edge of what is known and looked out at what is not, and you are not afraid. That is not nothing. That is, quietly, everything. Let the universe be large tonight without asking anything of you. Let the questions stay open without keeping you awake. Let the light bend and the clock slow and the boundaries hold. All of that, out there doing what it does, while you, in here, let go, completely, softly, without holding on to anything. The story is told. The night is yours. Now close your eyes and gently replay the universe you heard tonight, and rest.